discontinuities, we talked about the difference in a continuous versus discontinuous function. Okay, we mentioned limits, and we looked at the limit notation and what a limit is. Okay, remember the limit is the y value that you're approaching as you approach a specific x value. So we did some examples with limit notation. And then we distinguished between the three types of discontinuities. Okay, I actually want to add a little something here when we're talking about these. So this is on the back side. We said you have an infinite discontinuity, a jump discontinuity, and a removable discontinuity. So infinite discontinuity means that the limit from the left and the right are going on indefinitely. Okay, so it's going toward infinity or negative infinity. Okay, so as x equals at x equals c, the function value increases or decreases indefinitely. Okay, and so then it keeps going and going and going. Okay, that means there's an asymptote there. Okay, then the second option was the jump discontinuity, and it happens when your left limit, so as we approach a specific x value, in this case c, as we approach from the left and as we approach from the right, we're going to two different y values. Okay, and we said, so the limits from the left and the right are different. Now, what I want you to add there is that means if the limit from the left and the right are different, the limit does not exist. If the limit from the left and the limit from the right are different, the limit does not exist for that at x equals c, or as x approaches c, I should say. Okay, now at a removable discontinuity, we looked at the limit from the left and the limit from the right. They were the same. They were both approaching the same y value, okay, but there was a hole there. Okay, so when that happens, okay, the limits from the left and the right are the same. If the limit from the left and the right are the same, then your limit does exist. The limit exists. And it is whatever the limit from the left and right were. Okay, mathematically speaking, that would look like this. You would say the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right. So we use a little minus or a plus to indicate left and right. Okay, if those are equal, then that equals the limit as x approaches c, with no indication of left or right, just the overall limit. So if the left limit is equal to the right limit, then that is the overall limit. Does that kind of make sense? I think we're going to do some examples on the sheet I just passed out to you. It's going to make more sense if it's not super clear right now. Okay. So then we practiced identifying the types of discontinuities, and we gave the three conditions of continuity. Okay, the formal definition. The function has to be defined at that c value. Okay, so that means it has to be in the domain. Okay, the limit must exist, meaning the limit from the left is equal to the limit from the right. And then if both of those happen, those need to be equal to each other. The function value, okay, wherever it's defined at x equals c, that has to be equal to the limit. So the limit has to equal the function value when you evaluate at c. Okay, so if all three of those are true, then it's a continuous function at that point. There's no discontinuity at that point if all of this is true. So is everybody good with that? Okay, so now I want us to go back. Now with this knowledge from those notes, I want us to go back to that exploration page where we were talking about the gas prices. We were trying to make predictions using the graph, and then we tried to make predictions using the table, okay? But I just want to now, I'm going to add limit notation to these. So you can see. Okay, so here, when it says looking only at the gas prices before March 11th, if here's March 11th, if we're looking before March 11th, that's on the left side, isn't it, of March 11th? So that's the limit from the left. So what are we approaching as we come from the left? So as a limit, I would say this is the limit as x approaches the 11th from the left. I'd put a little minus from the left. And we called this function g of t. Okay, so the limit as x approaches 11 from the left for g of t is 232. That's what that scenario means in limit notation. We said as we look coming on the graph to the left of March 11th, everything leading up to March 11th, we think this is what it's approaching, what gas price it's approaching, and that's your y value. That's your limit. So when we were looking at the prices after March 11th, those were to the right of March 11th in the graph. We would write that as the limit as x approaches 11 from the right of g of t is 204. Again, if you're watching this as a video, your prices for your class may have been slightly different because these were estimates, and I kind of let the class pick what they wanted to settle on as their estimate based on that graph. Okay, it would have been close to these numbers, but it might have been slightly off. Okay, now part C had asked if we were confident that we could pinpoint the exact price or how confident we were, and we said not very confident. That's because the limit from the left did not equal the limit from the right. So the limit did not exist. That's why we were not confident in making a prediction. Does that make sense? Okay, then we did a similar, actually, let me highlight those colors to color code that. Left was supposed to be the blue, so let me switch that real fast. Okay, so coming before March 11th, that meant coming from the left, so we used the minus there. And then after meant we were coming from the right, so we did the plus sign there. Okay, so now in the table, coming from the right was this arrow here. So we're looking at these numbers from the right. And then we were looking at them, the y values from what we were approaching coming from the left. And then we were wondering if we could make a reasonable prediction. So I would say my limit as x approaches 11 from the left, and this was a year later, this is a different function. So let's call this one, since we called the other one g of t, let's just call this f of x so that it's not exactly the same. So what did we say we were approaching? What y value did we think as we were coming from the left? What price were we approaching? 243. Okay, and then when we did that from the right, that would be the limit as x approaches 11 from the right of the f of x. What did we say those prices were approaching? Also 243, right? So here in this example now, the limit from the left and the limit from the right are equal. So that means the limit does exist. Do y'all see that? So that's why in this one, we said, yes, we are confident we could make a reasonable prediction because the limit exists. The limit from the left and the right are equal. We're confident in making a prediction. Now, our prediction wasn't accurate, apparently, but that happens sometimes. That would be like a removable discontinuity. Like you're approaching the same point from the left and the right, but it's not there. It's somewhere else. It's been removed from where you would expect it to be and placed somewhere else. Okay, this would be an example of that removable discontinuity. Does this make sense? Does that kind of help put it together? What we did in that lead-in activity and now what it looks like in limit notation? All right. So then I want you to get out the paper that I just passed out to you, which on one side it says check for understanding. And on the other side, it says, it has like at the top a quick notes box. It looks like this. That's the side I want you to be on. Yeah, I haven't seen it, but you can look around. Okay, which 3? 1 or 3? Which one do you want to do? Didn't you already do 1 earlier this morning? It was 5 questions? That was 1, so 3. Okay. All right, y'all give me 1 sec. Hold on real fast. So if you read through that quick notes right there at the top, that's just a recap, like a synopsis of what we talked about in our notes, what we've said about limits. It says that what a limit is, it's you're getting closer and closer and closer to a specific Y value. That's what your limit is. Okay, as you approach any given X value, the limit is the corresponding Y value you're approaching. And then it goes over the limit notation. And then I've highlighted, I've tried to color code for you, excuse me, the overall limit versus the left limit and the right limit. Okay, so you can see blue is what I'm going to be using for the left side limit, yellow for the right side limit. And who remembers their color combinations? What do you get when you mix red? I don't even know why I said red. Blue and yellow. You get green. Okay, so if the left side limit and the right side limit are equal, then we get our overall limit. Does that make sense? The left and the right limits have to be the same for you to have the limit, for it to exist. Okay, so here's a little scenario about getting a bride and groom to an engagement party and some nightmares somebody's having leading up to it of things that could go wrong. So we're going to look at some different scenarios. Okay, so nightmare number 1, you can see the little guy drawn here. That's the groom, and this little lady is the bride. So we've got the groom, they're trying to get to Olive Garden, and he gets there, nobody's there. Oh no, he went to the wrong location. Okay, so let's look at this. What is the limit as we approach, as X approaches 1 from the left? Okay, remember that blue means from the left. Okay, the yellow means from the right. Okay, so the groom is coming in from the left, and as he gets closer and closer and closer to the 1, that's where the Olive Garden is, what Y value is he approaching here? What's the Y value there? We can just estimate. It doesn't have to be perfect. Anybody can participate. What is the Y value here? Well, you can see where I drew. 1 is up here where it crosses 1 here, so it's coming down below that. So I would estimate what? What do y'all want to estimate? Sure, half. As we get closer and closer and closer to the x value of 1, we're getting closer and closer and closer to the y value of 0.5. Remember when you have the little wavy equal sign? That means approximately. So it's about 0.5, okay? We don't need to be exact. We're just grasping a concept here, okay? And then the bride's coming in from the right. As she's getting closer and closer and closer to the x value of 1, what y value is she approaching? Sure, we could say 1.5. It looks a little bit closer to 2. If you want to say like 1.7, 1.8, it doesn't really, it looks like more than half. Some of my classes were like, can we just say 2? And I'm fine with that because this is just an estimate. But if we want to mark it in here, we can say about 1.8. That's fine. Okay. So are those the same numbers? No. So that means the limit from the left and the limit from the right are not equal. What did we say that that means? Can we combine our yellow and blue to make our overall limit? No, because they're not the same. So that means that the limit, what phrase did we put in the notes? What did I say? It was when we talked about look at jump discontinuity. Does not exist. Good. And now I'm going to abbreviate D-N-E from here on out. I'm not going to write out the whole phrase, does not exist. Okay, so D&E, it does not exist if the left and right limit are not the same. Okay, now then part D wants us to actually evaluate the function at f at 1. So what is f of 1? Okay, so we say, okay, I go to x is 1. Where is my function? At what y value? Where it's solid, right? Okay, so what is that? What did we estimate a minute ago? We said about 1.8. All right, so if you think about that, those conditions of continuity that we talked about, this meets the first condition. It exists, that it is defined at x is 1. The function is there, it's in the domain. 1 is in the domain of this function. So condition 1, check. Okay, condition 2, the limit exists and does not. Left and right were not equal. So this fails the continuity test. So this is a discontinuity. Can you tell me what type of discontinuity it is? This is a jump, and I'm just going to list that in the margins out here. I'm going to put the type. I'm either going to write continuous, if it's continuous, or I'm going to put the type of discontinuity. So this is a jump discontinuity. All right. Scenario number 2 is you successfully get the bride and groom to the restaurant with all the guests, but the chef doesn't show up. Okay, so we're looking for as x approaches -1 is the limits we're looking at. So our groom, as he gets closer and closer and closer to x is -1, what y value is he getting closer and closer and closer to? 1. Good. Okay, and then from the right, because the bride is coming from the right, as she gets closer and closer and closer to the x value of -1, what y value are you getting closer and closer and closer to? To what? It's that same height, right? That same hole is what they're approaching. So it's the same y value of 1. So what does that mean for our limit? That it means that the limit exists, right? So what is the limit? If the limit from the left and the limit from the right are equal, what's the overall limit? It's what those equal. It is the same. Okay, so the limit exists. It's a 1. All right, so this meets condition 2 of continuity. That's good. Let's check condition 1, which was that it is defined at that c value, in this case, -1. So if I go to -1 and I'm looking for my graph, Where's my graph here? Is it defined anywhere? Is there a point on my graph that it exists at x is -1? No, it's an open circle, and it's not like it's been replaced anywhere else, has it? Okay, so this fails condition number 1. This is not defined, it's undefined. So we did have a limit, but we didn't evaluate it. That was undefined. Okay, so this is a discontinuity. What type of discontinuity is this one? This is a removable. You have a hole, it's a removable discontinuity. All right, nightmare number 3 was that the bride canceled as they were getting close to the restaurant, so they veered off and changed directions. Okay, so we're looking as we approach 1. Okay, so the groom is coming in. Oh no, he hears the bride canceled, so he veers off, right? He doesn't go to the Olive Garden. Where is he approaching? What y value? As we get closer and closer and closer to x is 1, what y value are we getting closer to? Yeah, we're going down to what infinity? Negative infinity. So from the left, the limit's negative infinity. Now from the right, the bride's coming in. She's the one that decides to cancel. Wonder what happened. Okay, where's she going toward? What y value? Positive infinity. All right, are those the same? No, and even if they were, I want to point this out. They're going toward infinity. Is infinity an actual value, an exact value? No, it just indicates that we keep going indefinitely, right? So even if they were both going toward positive infinity or both going toward negative infinity, the limit here would still not exist. If they were both positive infinity, you could write infinity as the limit. Or if they were both negative infinity, you could write negative infinity. Okay? But I want you to understand the concept of the fact that infinity actually means the limit does not exist. Because let's think about a limit. Like you have a credit card limit. You're trying to spend over your limit. You're going to get declined, right? Okay? Because you've reached your limit or you're close to your limit, okay? And you can't go over it. Okay? It is a boundary. If we're going toward infinity, is there any boundary? No, it keeps going. There is no limit. Okay? No limit soldiers, right? They keep going. There's nothing stopping it. Okay? No boundary. So technically, infinity and negative infinity technically do not exist. The limit does not exist. We good with that concept? Okay. All right. So then evaluate here when x is 1. So we go to where x is 1. Is the function defined anywhere? Does the function exist anywhere along that x value? No. So this is an undefined value. Okay, I have people asking, when do I use undefined? When do I say does not exist? If we're evaluating, we're going to say undefined. If we're talking about the limit, we're going to say does not exist. Okay, so that's how we're going to distinguish between those two. I might have mentioned this the other day, I don't remember, but the limit does not exist here when you're approaching two different numbers, and technically the limit does not exist here if you're going to infinity or negative infinity. So two different scenarios where we could say the limit does not exist. Okay, so that's on our, what type of discontinuity is this one? Infinite. So at an infinite discontinuity and at a jump discontinuity, the limit does not exist. Okay, the limit can exist at the removable though. Any Mean Girl fans in here? Y'all remember that scene? She's in calculus. She's like, oh, the limit does not exist. Okay, so that's what we're doing. It's going toward infinity. It technically does not exist. All right. Last but not least, in actuality, this little engagement party goes off without a hitch, and they live happily ever after. Okay, so let's break down this scenario. So we're approaching 5. X is approaching 5. So I'm actually going to do part D first because I want to put a point on here for you to visualize where we're approaching. So when X is 5, what's the Y value on this graph? 0. Okay, so we're going to go ahead and answer that one. It's 0. I'm going to put a point there so you can have a good visual of what we're approaching. Okay, so as the groom is coming in from the left, getting closer and closer to X is 5. What's Y getting closer and closer to? 0. Good. So the limit from the left is 0. Okay, and then the limit from the right, that's our bride, she's coming in. As she gets closer and closer and closer to X is 5, what's the Y getting closer and closer to? Also 0. So what does that mean for your limit? That it does exist, and what is it? It is 0. Good. So first condition of continuity, the function is defined at the value. So f of 5, we have a value, 0. Good, check. Second condition, the left limit and right limit are the same, so the limit exists. Check. Third condition, the limit and the function value are equal. Is that right? Yeah, they're both 0. Check. This is a continuous function at x equals 5. There is no discontinuity here. This is continuous. So that kind of answers that question at the bottom. It says only one of these is continuous. That would be number 4. Okay, you can put in your own words what your reasoning for y is. You could say it meets the 3 conditions of continuity, or the limit is equal to the function value, or explain it in whatever words you want to explain it. It's your notes. You need to be able to look back on that and understand what you meant. Okay, so put that in your own words. How do y'all feel about limits right now? Pretty good? All right. So on the back of this one is a check for understanding. It's 4 questions. I want you to kind of treat that as like a little study guide for the quiz tomorrow. Piecewise is also on the quiz, what we did a few days ago. That piecewise delta math is due tonight. So if you have not finished the piecewise delta math, I would work on that. Make sure you get it in before midnight. But then you can work on that. You can work on that delta math, or you can work on those check for understanding questions. The check for understanding questions are not a grade. That paper that we were just working on, I want you to keep it with your notes. But the quiz is not super long tomorrow, so I'm going to take a few minutes at the beginning of class before we quiz to go over any questions that you have on that check for understanding. So give it a shot, and then tomorrow you can ask questions if you have any, and then we'll take our quiz. Okay, now what is for a grade for limit practice is this delta math, limits and continuity practice. So the piecewise that you had already been assigned and hopefully been working on is due tonight. The limits and continuity one, that's the new one, is not due till Monday night. Okay, so you have time. You don't have to do it tonight, but I might try a few to get ready for that quiz tomorrow if I were you. All right, so let me stop this recording.